Hey guys, welcome to the OneClass channel. My name is Sydney and I'm currently a third year engineering student. Today we're going to be going over some commonly asked math questions at both the high school and university level. If you need some additional homework help or tutoring, please check out the links in the description below. And let's get started. Okay. So the first question is asking, if x squared plus x times y plus y cubed equals 1, find the value of y triple prime at the point where x equals 1. So this is an implicit differentiation question, and it's asking for the third derivative of y. So we're going to do this question in multiple different steps so that we can find y triple prime as the final answer. So we're going to start by working with just the original equation that's given. That equation is x squared plus x times y plus y cubed equals 1. And what we're going to do is sub in x equals 1 as it's given. So that's 1 squared plus 1y plus y cubed equals 1. Okay? Obviously we can simplify from there. Y cubed equals 1. Equals 1. And since we have 1 on either side, you can subtract 1 from both sides and they cancel out. You're left with y plus y cubed equals 0. And we can factor out 1y, so it becomes y times 1 plus y squared equals 0. And this will give you two different solutions. So we get y equals 0 since we're just taking the two different parts separately. And we have 1 is equal to, 1 plus y squared equals 0. And then you can rearrange it and we can get y is equal to square root of -1. Or you can also say I is equal to I, the imaginary number. You can also use j if that's what you're more familiar with. And so we're not going to use that as one of the solutions, but we are going to use y is equal to 0. Okay? So now we're going on to the next step. The next step for this question is to take the derivative of the original question, the original equation. So let's by dx actually times, or not times, the derivative of the equation. So I'm going to do both sides of the equation plus y cubed equals, and then on the other side we have the derivative of 1. Okay, so new step here. All right, so let's start on the right side. That's pretty simple. We know the derivative of a constant is just 0. And then we're going to work through the left side now. I'm going to write down some rules that will help you with the differentiation. So first we have the power rule. And that tells you that the derivative of x to the n, or x raised to an exponent n, is equal to n times x with the exponent n minus 1. All right? And then we also have the product rule. And that states that if you have two variables multiplied by each other, in this case we're going to use the variables u and v just as placeholders, you get the derivative of the first times the second plus the first as is times times the derivative of the second. Okay, we're going to use these to solve what we came up with up at the top here. And it doesn't matter which one you take the derivative of first when you're doing the product rule, but that's the way that I like to do it. Okay, so back to the derivative of the equation. We're going to do each term individually. Okay, so first we have the derivative of x squared. So using the power rule, we can see that it's 2 times x and then n minus 1. In this case, it's 2 minus 1. So you have x to the 1 or just x. Okay, next is the derivative of x times y. So you can use the product rule. And so we'll take the derivative of x first. So that's dx by dx times y just stays the same, plus x stays the same, times the derivative of y. I'm just going to put that in brackets so that you can see that that is just for the term x times y. Okay? And then now we're going to take the derivative of y cubed. So that we're going to use the power rule again. We get 3y, and then 3 minus 1 is 2. And because we're taking the derivative of y with respect to x, the dx is on the bottom, we have to add in another term, okay? We have to add in dy by dx, just acknowledging that we're taking the derivative of y in here, okay? And then that is all equal to 0 because we determined before that the derivative of a constant is 0. Okay, so I'm just going to change notation so it's a little bit simpler to see. I'm going to change it to the prime notation to simplify this equation. So we have 2x plus, and then this here is just dx over dx. So that's 1 times y plus x, and then this is what I'm trying to say here. The first derivative of y, I'm going to write now as y prime, okay? That's the first derivative. These are equivalent forms of the same thing. Plus 3y squared, and then the first derivative of y is equal to 0, okay? Now at this point, we are ready to sub in the known values, the things that we already know. So from the question, it tells you that x is equal to 1. And now we also found out from before that y equals to 0. So that will help us. We can set y equals to 0 as well. So then we get 2 times 1 plus 0 plus 1 times the first derivative of y plus 3, 0 squared, or of course you don't have to, you can just ignore this term since it all turns into 0 here, and this one also is obviously 0. So we're only left with 2 terms left. We're left with 2 plus y prime is equal to 0, or that is y prime is equal to -2. That's the same thing as saying the first derivative of y is equal to -2. Okay, so now we are ready to go on to the next step. What we're going to do is actually take this equation up here before we subbed in any of our values, and we are going to take the derivative of that again. So basically the point of taking the derivative of this equation multiple times is to get the y triple prime we are looking for that the question asks. So here we go. Taking the derivative of that, oops, keep writing y, of that equation, I'm switching back the notation to dy by dx, since we're using the dy by dx here. I just think it's a little bit easier to visualize. dy by dx. If that's too confusing, the switching back and forth, then just leave it as the notation that you prefer. Okay, and since it's 0, we don't have to take the derivative of the right-hand side. It just remains 0. Okay, so now we are ready to take the derivative again. So we're going to have to use, well, I'll say that when we get there. The first term is just 2. We're using the power rule here. So since we can imagine this as x to the power of 1, taking the 1 out in front and multiplying the 2 by 1 is just 2. So that stays the same. And then we know it's x n minus 1. And since 1 n is 1 in this case, it's 1 minus 1, which is 0, which is 1. So all you're left with for this the derivative of this first term is just 2. Okay? Plus the derivative of y, dy by dx, plus, okay, here we have to use the product rule for this term. So taking the derivative of the first part of that term is x, so dx by dx, and then the dy by dx remains the same, the second half of that term. And then, remember, we have to do that again. So x stays the same, and now you're taking the derivative of the second term, which is the second derivative now of y. Okay, I'm running out of room quickly here, so zoom out a little bit. So now we are on to this term, and we're going to do that again. So I'm going to group the 3 and the y squared together as one term, and then treat the derivative of y as a second term. Okay? So the derivative of this, we would start with the derivative of the first term. So that's 6, or you can look at it as 3 times 2. That's the exponent. We'll choose the exponent from the y, and then y to the exponent of just 1, because we had 2 originally, minus 1 is 1 for the exponent. And then since this is y, let me just look here. Yeah, since we're taking the derivative of y here, remember just focusing on the derivative of this first term, we have to add in the additional dy by dx, okay? Acknowledging that we're taking the derivative of y and not x, okay? And then the second term here, a lot of arrows, but the second term is going to stay the same. Whoops, sorry about that. Hit that with the side of my hand. Okay, the second term, this term is staying the same. Hopefully that makes sense. It's a lot to deal with at the same time, I understand, but that's the first. So looking at the power rule from before, or sorry, the product rule from before, I can't see all of it. You have to take the derivative of the first term times the second term as normal, and then add the first term as normal times the derivative of the second term. Okay, so that's what we have to do next. So first term as normal, and then the derivative of the second term. So that's the second derivative of y. I didn't write. So that's the notation for saying the second derivative of y. You just write the squared beside the d and squared beside the x in the denominator. All right, a lot going on. Let's simplify this a little bit. So we have 2 plus, and I'm just going to change the notation back once again because I think it looks a little bit simpler. Plus, this becomes 1. We just have dx over dx, which is 1. Plus first derivative of y plus x times the second derivative of y, which is the same thing as y double prime, plus 6, that's that, y, and then this here. So when we're combining the derivative twice, it's not the same. You can't write it as the same notation as the second derivative, okay? Just make sure you don't do that. It's the second derivative, or sorry, the first derivative squared. Just make sure you don't get that confused with like this notation, for example. You can't square them. So then for this term, we have 3y squared, and the second derivative of y, or y prime, equals to 0. Kind of looks like a 4. Okay, so now that we're at this point, we're ready to sub in our known values again. So we have x equals to 1 from the question, y equals to 0 from that first step that we did, y prime is equal to minus 2, that's just up here. Okay, and let's sub those in. So we have 2 plus minus 2 plus minus 2 again. Of course, you can combine these if you want to. I'm just skipping that step. Plus 1 times y double prime plus 6, y is 0, y prime is minus 2, yep, squared plus 3, y is 0 squared, and y double prime equal to 0. So there's a lot of zeros. You cancel out this term, that whole thing is 0, and this whole thing is 0. And then this, add that together, that's minus 4 plus 2 is minus 2, plus, and then all we have left, all we have left is that term, so that's just y double prime is equal to 0, and that will give you the answer of y double prime is equal to 2, or the second derivative of y is equal to 2. Okay, I think we are on the last step now. My mouse is over there. Okay, we're on to the last derivative of our equation. So we're starting from this equation for the last step before we subbed in the values of x, y, and y prime. And we are taking the derivative of that. So 2 plus y prime plus, well, you can combine those y primes. So it's 2y prime, x, y. Oh, I forgot. I was going to change notation again. Here we go. Second derivative of y plus 6y dy by dx. So I'm just rewriting the equation. 3y squared is the second derivative of y equals to 0. Okay? So we have something new here. I'm going to write down the rule for this part, for this term in the equation. I'm writing down a new rule. It's called the chain rule. And that states that the derivative of a function with an exponent n is equal to n times the function to the power of n minus 1. So that's just the normal power rule, as we've seen before. But since this is a function, an unknown function, we also have to take the derivative of that function, okay? That prime notation is just symbolizing that that's the derivative, okay? So I'll go through the first part of this, and then once we get to this term, I'll go through what that means a little bit further. Okay, so the derivative of 2 is 0. Next term, 2 times the derivative of first derivative of y. Well, the derivative of that is the second, 2 times the second derivative of y. For this term here, we can apply the product rule. I feel like I probably said that backwards a couple of times. Product and the power rule sound similar, but okay, so this is the product rule. So we take the derivative of x first, times the second term as is, plus the first term as it is, times the derivative of the second term. So that's the third derivative of y now, the derivative of this term here. I'm going to run out of room again. We're getting long. Okay, so now we're on to this term. And we have to apply the chain rule. So that means we are going to, well, we not only have to apply the chain rule, but we also have to apply the product rule. So, one big bracket around that, and so we're taking the derivative of 6y first. So that's 6 dy by dx, and then dy dx squared, that stays the same, plus 6y, and now we have to take the derivative of dy by dx squared. So that's when this chain rule comes into play. We have the 2 out front, which is the n, times dy by dx, and the exponent here is 2 minus 1, or just 1, times, now we're looking for the derivative of what's inside the brackets, which is the second derivative of y. Well, we still have one more term here, okay? I think there's a bracket there. Sorry if this is getting confusing. It's a lot of terms to keep track of. So then we have the derivative of 3y squared, which is 6y times dy by dx. I think we've done something similar to this already. Times, well, this stays the same, that's the second term, plus the first part of the term. Oops, I think I just made the screen a little smaller. So, okay. The first part of the term stays the same, and then we take the derivative of the second part of the term. Oops, so 3. Running out of room. All right, let's try to look at everything all at once. There's a lot. Okay. I'm going to change the notation again and simplify this a little bit. So don't have to worry about the 0 at the beginning. So that's 2y double prime. I'll write this a little bigger. 2y double prime plus, this is 1y double prime plus xy triple prime, that's that term there, plus 6y prime y prime squared, plus we have 2 times 6, 12y prime y double prime plus 6y y prime y double prime plus 3y squared and y triple prime equals to 0. Okay, lots of terms. Before we sub things in, I'm just going to double check I haven't went wrong anywhere. I don't want to, yeah. So what we could do is combine these two together since, well, we know y prime squared is just y prime times y prime. So this becomes y prime cubed, but that's not necessary because we're just subbing in a value for that. Double checking. All right. Let's start subbing in values. So let's sub in what we know. We know x is equal to 1. From the beginning, we know that y is equal to 0, y prime is equal to -2, and then just from the previous step that we did, we know that y double prime is equal to 2. So we have 2 times 2 plus another 2 plus x times y triple prime, which we don't know yet, plus 6 y prime and y prime squared plus 12 times 0 times y prime times y double prime plus 6 y, oh no, I'm running out of room again, 0, which is y prime, y double prime, plus 3 y squared, and y triple prime is equal to 0. Okay, a lot of these are 0 because it's multiplied by 0. So we're left with just these. The beginning, so we have 2 times 2, it's 4, plus 2, plus y triple prime, and then this term here, 6 times y, or sorry, no y's, -2 squared, which is 4, times minus, so we have minus 12 times 4, okay? And that's 48. And then, oh, but it's a minus. I wrote a plus out here automatically. So it's a minus 48 equals to 0. And that will give you the answer if you move everything over to y triple prime equals 42. And that's your final answer. So it's a long step process, but we're finally here. Yep. So just looking through what they've done here, I noticed that they ran into a problem on step 5 where they got a different answer for the y double prime. So I just made note of that, saying that there was an error in step 5, and the correct solution is 42 as we found over here. So let's move on to the next question. Next question asks what the derivative of an absolute value function is. So let's say question 2. So first let's look at what an absolute function actually is. So an absolute function, or an absolute value rather, is the notation that shows that the value will always be positive in magnitude. Looks kind of like that, right? So that shows that x, well, or that x with this notation will always be a positive value, positive x, okay? Well, I guess I should say the value inside of the notation can be negative, x can be negative, but the result after the absolute value brackets are applied is a positive number, all right? So we're looking for the derivative of that. So we'll remove this example here. So this notation can also be written as the square root of x squared, okay? You can also write that, as we know, a square root can be written as an exponent of 1 over 2. and that will help us when taking the derivative, because it's a little bit easier to see as an exponent, because we know this is the power rule, or sorry, yeah, the power rule, but also the chain rule, because we have a power on the outside plus a function on the inside of the brackets, okay? There we go. So applying what we know about the chain rule, we're going to take the 1/2 out in front, keep the function in the brackets as is, and then go take the exponent, which is 1/2 minus 1. That's n minus 1 for the exponent. And then, using chain rule, we're next going to take the derivative of the function on the inside of the brackets, which in this case is 2x. All right, these cancel out, and the 1/2 minus 1 is minus 1/2 times x. Since it's minus, you can also write it in the denominator, and that will make the exponent now positive, x squared 1/2. Or, of course, you can write the 1/2 as a square root again, so you can visualize that. And as we stated at the beginning of this question, that is the same thing as the absolute value. So the derivative is equal to x over x, the absolute value of x. The derivative of the absolute value of x is equal to x over the absolute value of x. Okay. Going through this solution here, they came up with the same thing. So we're good to go. Just going to leave a comment. Oops, that's correct. And we can move on to the next question. Question 3. So it's asking, how do you convert the parametric equations into Cartesian equation, a single Cartesian equation, by eliminating the parameter r? So here they give you x is equal to r squared plus r, and they also give you y is equal to r squared minus r. So basically, our goal here is to get rid of the r's completely and just have an equation that contains x and y. So we can do this in a couple of different ways. I'm going to start by rearranging each of these equations that, since we notice that these both have an r, they also both have an r squared, but we're going to start with this. I'm going to rearrange for r so that I can set them equal to each other. All right, so y minus r squared equals, I'll write this the other way, r squared minus y is equal to r. Okay, and I'm going to set this equal since they both have r isolated. So if r equals to r, we have x minus r squared is equal to r squared minus r. And now I'm going to rearrange so that we have r on one side of the equation and then only x and y on the other side of the equation. So rearrange, we have x plus y is equal to r squared, and then we have r squared is equal to x plus y divided by 2. Okay, now that we have r squared, I'm also going to try to find out what the product of x times y is. And that will help us sub in for r squared. I think you'll be able to see a little bit better what I'm trying to say when I show you. So, from the equations that we know, we'll sub in x and y. So this is x times y. That's y. So we're just going to do simple multiplication with brackets. So r4 minus r cubed plus r cubed, and last one here is minus r squared. So r cubes cancel each other out because we have plus and minus, and we're left with r4 minus r squared. Okay, so since we already found out what r squared is with x and y, we can rewrite this as r squared to the power of 2, which is, as we know, the same thing as r to the power of 4. And then that way we can sub in r squared with what we found out before here. So that's x plus y divided by 2 squared minus x plus y over 2. I hope I'm not cutting too much off here. Okay, so, well, the denominator we have 2 squared, which is 4, and then I like to think of the little saying, square the first, square the last, and then in the middle we have the first times the last and doubled. Minus, y divided by 2, that just stays the same. And don't forget we have an x and y on the other side. And then, because we have 4 in the denominator and 2 in the denominator, we want to get rid of denominators completely, so we're just going to multiply the whole thing by 4. So we have 4xy is equal to x squared plus 2xy plus y squared minus, well, if we multiply this by 4, this becomes 2, right? Oops. So 2x plus y. Alright, now we can rearrange because, as you can see, we only have x and y left. So we have our final equation. We're just going to set it, rearrange it and set it to 0 so it looks like a normal Cartesian equation. So we have x times y on either side. So moving that over, we have 0 is equal to x squared minus 2xy plus y squared, and then I'm just distributing the minus 2 into the bracket, and we have minus 2x minus 2y. Alright, and that's your final equation. Of course, you can rearrange that if you have like a preferred arrangement for where to put the x's and the y's, but that is what we've got. Just checking the answer here. And we have all the same terms. We have x squared, y squared, minus 2x minus 2y, and minus 2xy is equal to 0. Great. Let me just leave comment. Okay. Good work. Correct solution. Okay, on to the last question for today. All right. This question asks, find the values of x for which the series, the given series, converges. And then it asks to answer the question in interval notation. All right, so what we are going to do is compare this given series with one that we already know. So we already know about the geometric series. I'm just going to write it down here so that it'll be easy to compare. So the geometric series is the sum of n1 to infinity, a times r, power of n minus 1, which is equal to a times 1 plus r squared plus r cubed plus etc. r to the power of n, n minus 1. And we know that this series, the geometric series, converges when the absolute value of r is less than 1. Okay? So what I'm going to do here is try to write out the given series so that it looks similar to this geometric series, so we can confirm if it converges like the geometric series does. So this is the series that we are given in the question, 2n, and we can start to write out the sum. So at n equals 1, which is where we're starting, according to the notation, we have x minus 3 squared times 2, and then if n is 1, it's just 2, plus the next term where n is equal to 2, we have x minus 3 squared to the power of 2 plus x minus 3 squared over 2 to the power of 3, and of course we know that goes on and on. Okay? So we can see that we can take out something common between all of these. So we see that the x minus 3 squared is common between all of these, but it also has 2 in the denominator, which we can also take out. And then we are left with 1 plus 1 over 2, because of course 2 squared is just 2 times 2, and 2 cubed is just 2 times 2 times 2. So we can take one of those 2's out from each denominator, and this is what's left over for this one, so that's 1 over 4, or you can also write that as 2 squared, plus, and then etc. basically. So you can kind of see that this, what we just came up with, that wasn't really a line, what we just came up with here looks very similar to what we determined up above, right? Just rewrite this over 2, 1 plus, if we say that 1 over 2 is r, then we'll have exactly this equation. All we have to do now is replace 1 over 2 with r, and this first value here with a, and then you'll get the same equation as the geometric series. So we can confirm that it will behave in the same way. That our series, the one that is given in the question, will behave the same way as the geometric series. So that means that it will converge when r is less than 1. Oops. R is less than 1. And we know r is, well, I'll just write it like this. R is less than 1. Kind of redundant, I guess, but 1/2 is less than 1. So makes sense. We know that this is a geometric series, and we can say that it will converge when r is less than 1. It's asking for the answer in interval notation, and this interval notation, I guess that's absolute value. You can write it in that way, or because it's absolute value, it's equivalent to saying this. So when r is greater than -1 or r is less than 1. Since absolute value, it allows for both positive and -1. So this will be the final answer. Oops. This will be the final answer, and we know that our series converges when r is in between the values of -1 and 1. So I think that's all we'll be covering for today. So if you found this video helpful, please leave a like. And if you want to be notified of when we do another Q&A like this one, just hit the subscribe button and the notification bell. If you want to submit any of your own questions, you can see the links in the description or just leave a comment below. And that's all for today. Thank you.